to the function, and it was x squared minus 4x plus 2. So x squared minus 4x and plus 2. And I want the window just to be between 1 and 4. I don't want to see anything else. And I left a negative 10 to 10. I don't care. So let's graph. And that's exactly what happens, because this piece is much bigger than this piece. The result of the entire area between 1 and 4 is a negative number. Is this okay? Good. Thank you. Okay. So finally, we can talk about the definite integral. So 5.2, the definite integral. And remember, the previous example was the area was negative 3 for the interval 1 comma 4, and the function x squared minus 4x, it was plus 2, correct? I just entered it, just making sure. Yes, it is plus 2, correct. Okay, so we know that the limit of the Riemann sum is limited to linear, quadratic, cubic. But what do we do with the rest of the functions? Can we determine the area? Can we determine, like we just did with the previous problem? Remember when we calculated the distance covered between 0 and 6 seconds? It stopped, starting from roughly 70 miles an hour, and we determined this area. It was a perfect application in which we were basically, we had the function but not explicit, and we wanted to determine the distance. The distance, by simply determining the antiderivative of this function and evaluated it, it was given us a very good approximation. It's still an approximation of the distance by finding the area. So what do we do with other functions? Well, the area, the exact area, as we know, is the limit of the Riemann sum from n equals 1. I meant to write I equals 1 through n. Of course, from delta x f of x I. But this is the same thing with the definite integral of the same function. It's still a sum, but this time we're not going to use the Greek letter s. We're going to use the Latin s, but elongated, stretched. It's a sum from, in this case, let me write a general form, from a to b. From what? From f of x dx. A long time ago, when we looked at something like this, we said that these two, delta x, the exact difference in x, or the differential of x, are the same number. But in an integral, I cannot use delta x. I have to use dx. In a limit of the Riemann sum, I cannot use dx. I have to use delta x. They mean the same thing. This is still this, the width of any subinterval. And f of xi is the same thing with f of x, from a to b. So how will this look for our function that we just finished calculating the area for? It will look like this. The integral from 1 to 4 from x squared minus 4x plus 2 dx. So this is the integral symbol. This is, of course, the lower limit. It has nothing to do with limits, as we know them. It's like the summation notation from a minute ago. This is the lower limit for the summation. This is the upper limit. It has nothing to do with this. Is where the starting point is and where the end point is. So this is called the upper limit. And the answer is always a number. So a definite integral is a number. It's the area under the graph between 1 and 4. Now, the question is, how do I determine this? Is there a way of determining the integral so that I don't have to go through the excruciating steps of the limit of the Riemann sum? Yes. And I would like to talk about it right now. Fundamental theorem of calculus. It has two parts. I'm not going to talk about the first part, maybe not today, but definitely on Wednesday or next week, but not the first part. I'm going to talk about the second part. So here's what we learned from the fundamental theorem of calculus. We learned two things. Let me write both things, and I'll tell you which one we're talking about right now. One, super important, is that differentiation and integration are operations. And I want you to tell me what word am I missing there. Although we're not going to talk about this part right now. We're going to talk about the second part. The second part teaches us how to evaluate a definite integral. This is what I want to talk about, so we can check our result from a few minutes ago. So what is the word that I'm missing here, first of all? Anyone?
I'm not sure. Inverse.
One reverses the effect of the other. Can I give an example of two inverse operations? Yes. The square root of an x squared. These are inverse operations. They will cancel their effect. If I apply this to this, I only get x. If I apply this to this, I only get x. Two other will be e to the x and natural log x. If I apply this to this, I get x. If I apply this to this, I get x. Same thing here. If I differentiate an integral, or if I integrate a derivative, I will get the function. Like in this situation or this situation. But this is for later. We're not going to talk about this right now. We're going to talk about this one. So there are two results, super important results of the fundamental theorem of calculus. One says that they are inverses, and we'll get to that. And the second one, it shows us how to calculate, how to evaluate a definite integral. And here is how. Whenever we want to determine the integral from a to b from f of x dx, what did we say the antiderivative, if I'm given function f of x, What is the notation for the antiderivative? So if I'm given f prime, I find f, right? But if I'm given f, what will be the notation for the antiderivative?
Capital F of x.
Excellent. So the integral from a to b from f of x dx is indeed uppercase f of x, the antiderivative of f, but evaluated from a to b, which really means f of the upper limit minus f of the lower limit. Super important result. This is what we're going to deal with for the rest of the semester. We're ready to calculate the same area using Fundamental Theorem of Calculus, Part 2. In some books this is Part 1 and the other one is Part 2, it doesn't matter. So the part that teaches us how to evaluate a definite integral. So, according to this, I have to find the antiderivative of this function. And when I'm done, I will evaluate it from 1 to 4. I will plug in 4 everywhere and subtract when I plug in 1 everywhere. But the question is, which function prime is that? Which function prime is this? And which function prime is that? So which function prime is x squared? And the answer is x to the third divided by 3 minus 4. Which function prime is x? Well, it's x squared over 2 plus. Which function prime is 2? Well, that must be 2x. I will clean it up a little bit by simplifying here. It's not that important. From 1 to 4. And now, according to this, I evaluate this function, the antiderivative, at 4, and I subtract when I evaluate the same function at 1. Plug in 4. 4 times 4, 16 times 4, 64 divided by 3, minus 4 times 4, 16 times 2 is 32, plus 4 times 2 is 8, minus, put parentheses so you don't forget that you have to distribute a negative sign. I plug in 1 is 1/3 minus 2, minus 2 plus 2. Okay. So I have 64 divided by 3 minus 24 minus 1/3, but these two go away. 64 over 3 minus 1 over 3 is 63 over 3 minus 24, but 63 over 3 is 21 and minus 24, and we are back to our negative 3 in a much more elegant way and much easier to work with. And we can determine now for any function we want with some restrictions, of course, because there are situations in which we can determine the antiderivative by hand. So for example, do whatever you want for any limits, lower and upper. If you try to determine this, you will not be able to find it without a computer software. We can't find the antiderivative for this. We can estimate it, and we will estimate it using the midpoint rule. And we will do that. I promise. I probably will get back to it today. Or any function for which we can determine the antiderivative. But for functions that we can determine the antiderivative, this will be carved in stone. If we can determine the antiderivative, we can plug in numbers and get this. So I'd like to practice with a few more examples. The Fundamental Theorem of Calculus Part 2. And then go back and talk about properties of this. Because of course, every time something is invented, as you know, properties will definitely follow. So I want to choose a couple of problems. Like for example 32 on 395. We are given the integral from 0 to pi over 4 from secant theta, tangent theta, d theta. We couldn't do this with the limit of the Riemann sum. It's a definite integral. I know the answer must be a number. I'm only asking myself, which function prime is this? Once I have the answer, the problem is almost finished. And in the meantime, I'll wait for you and I'll get some more water. I've been talking since 1 o'clock today. So which function prime is secant tangent? And the answer is anyone?
Is it secant?
Very good. So when I plug in pi over 4, I get secant pi over 4 minus secant 0. That's it. So let's calculate. I know that secant is 1 over cosine. So this is 1 over cosine pi over 4, which is the square root of 2 over 2. And this is 1 over cosine 0, and cosine 0 is 1, so this is minus 1. I will flip this, and I get 2 over the square root of 2 minus 1. I need to rationalize by the square root of 2, so 2 the square root of 2 divided by 2, minus 1, so the square root of 2 minus 1. Simple as that. Yes, at least one more, maybe two, and then we'll continue with properties of the definite integral. I would like to look at, yes, 37 on the same page. $3.95. And we have the integral from 0 to 1 from x, I think it's x to e, plus e to x dx. I'm going to look carefully. Yes, x to e plus e to dx. Very good. Okay. So I need to find the antiderivative and then plug in 1 and subtract when I plug in 0. Which function prime is e to a number? Well, that must be e, it must be x. Which function prime is x to a number? It must be x to that number plus 1 divided by that number plus 1. Plus, which function prime is e to the x? That's the nicest of all. So now when I plug in 1, I get 1 raised to 3.7, still 1, over this. Plus, when I plug in 1, I get e. And now minus, when I plug in 0. 0 raised to this number is 0, over this is 0. So if you want, just write 0. And plus e to the 0 power, which is 1. So that's our final answer. We don't have to do anything else. Okay, so let's look at one more. 39 caught my eye. Do we get the idea of how this works so far, in principle? So 1 over the square root of 3 to the square root of 3 from 8 divided by 1 plus x squared dx. Notice that basically this is dy, f prime of x dx. That's why I emphasized in the previous chapter that f prime does not equal dy. dy, say it again? Okay, so dy is the differential of y, f prime of x dx, so f prime does not equal dy. Please remember that, we discussed that in the previous chapter. Okay, so we want to find the antiderivative. Of course, like with anything, limits or the summation notation, this has no place in there. It's a constant, and it multiplies the function. It can wait patiently till we are done. So then, which function prime is this? Arctangent.
Yeah.
Very good. Very good. Okay then, so it's 8. Arctangent square root of 3 minus arctangent 1 over the square root of 3.
Don't worry, just pray that the enemy's worse than you are.
Jed, can you turn off your volume? Or I can.
Oh, sorry.
No problem. I can mute you anytime.
I thought I was still muted.
That's okay, that's okay. Okay, so now let's find the arctangent of the square root of 3. I always tell my students don't bother with tangent, ever. Don't waste your time. Just remember that if this is the angle, sine and cosine for pi over 6, pi over 4, and pi over 3. Always easy to fill it out. 1/2, 1/2, the square root of 3 over 2, the square root of 3 over 2, and this is the nicest of all. So for every time, of course this is not the case for us, because the arctangent will be 1. So we either have this or this. So when it's 1 over, so sine over cosine for the pi over 6, when it's this over this, it's that case. How do I know? Because it's 1/2 over the square root of 3 over 2, I have to copy the numerator and flip the denominator. So I get 1 over the square root of 3. So this must be the first angle, the tiny one. There is no calculation needed here. Obviously it's the second one, the bigger one. So I have 8 in parentheses pi over 3, because when I divide this by, this by this, I'll get the square root of 3, minus pi over 6. I still have to perform the calculations, it's not done. So I have 8, the least common denominator is 6, and this needs to be multiplied by 2. 2 pi minus 1, so it's pi over 6. I'll simplify by 2, so it's 4 pi over 3. And that's the final answer. That's the number that represents the area under this graph between these two numbers. 4 pi over 3. Any questions?